Hey everybody, it's great to see y'all. It is Mr. Prevet back again with another FRQ review for you guys. Excited to go through this one. Another calculator question from the 2022 AP test. This question, we've got a couple of graphs going to be dealing with some volumes, some related rates, some area between curves. I think a really helpful question in growing our understanding of calculus, which is the goal of this, right? So let's take a look at this question together. So it says let f and g be functions defined by f of x equals the ln of x plus 3 and g of x equal x to the fourth plus 2x cubed. The graphs of f and g, shown in the figure above, intersect at x equals -2 and x is equal to b, where b is greater than 0. So we've got these two curves. They give us the graph, and one of them is f, one of them is g. I would say if I were to do a simple sketch of these, I don't know how helpful this will be or not, but we've got something kind of looks like this. And we have two functions, right? We have ln of x plus 3. I'll do just y equals that. And our other function is y equals x to the fourth plus 2x cubed. That one's f, that one's g. F of x is going to be this upper function, ln, right? That's the shape of a logarithmic curve. And the curve of the bottom one, that is kind of what a quartic looks like whenever you have a cubic term in addition to it. So just to be clear, this top function is going to be f of x. This bottom function is g of x. If you really needed to know, you could go to y equals, graph one of the functions, see which one was which, But let's move on. Let's look at part A. It says find the area of the region enclosed by the graphs of f and g. So we're trying to find all of that, right? Now we know that this point here on the left is equal to -2, right? They tell us. But what they do not tell us is the value of this point, which they called b. So our first step is going to need to be solving for this point b, right? We know at b, f of x equals g of x. So the ln of x plus 3 equals x to the fourth plus 2x cubed. Now, I have not really found a great way on the TI to just, plug in these functions and spits out an x value. But a really thoughtful way to solve this problem is by isolating 0. So I'll get 0 equals x to the fourth plus 2x cubed minus the ln of x plus 3. And if I graph this right side as a function, so I'll do x to the fourth power plus 2x to the third power minus the ln of x plus 3. If I graph this, my window's a little janky. We'll go from -2 to, our graph gives us 2, so I'll do that. Our y minimum is way off, so we're going to need to switch our window. I do that by going to zoom and then zoom fit. That really works well for me. Oh, that still isn't great, to be honest. I might make my window from -2 to 1, because looking at our graph, we know our point is less than 1, but also greater than 0. It seems like something's going on down there. I just can't see what it is. Let's go down to zoom fit. Okay, now we get something that looks much more reasonable, right? And I know that when this function is equal to 0, these two functions are equal. So if I go to second calc and I go to 0, I can pick a left and right bound. So that's our left bound. This is our right bound. We get that our x equals b, is 0.782. So that is our rightmost bound, right? So now I'm trying to find the area between these two, right? And the area between these two we know is represented by an integral, the definite integral over our interval, which is -2, to b, which is 0.782, of our top function minus our bottom function. Now our top function we found was the ln function, so it will be the ln of x plus 3 minus our g of x, which is x to the 4th plus 2x cubed dx. And I can solve this using, if I go back to here, I have a really nice definite integral solver. So I'll go from -2 to 0.782 of, I gotta type all this out, the ln of x plus 3 minus x to the 4th plus 2x to the 3rd power dx. Now when I click enter, this should give me a value of the integral, which we get is 3.604, which is our final answer for the area of the region. So this one definitely a little bit complicated. We have to work on a couple of different things. The first one is that we have to actually find the point where they intersect, use a little bit of calculator stuff, right? But then we also have to know that the area between curves is the definite integral over our endpoints of our top function minus our bottom function. Now say we really mess this up and I switch these two. I did the bottom function minus the top function. Well, I would just get -3.604 as my value, and I would just take the absolute value of that, understanding that I had somehow flipped my answer choice. So the final answer to part A, 3.604. Tough question, honestly, for part A, which generally means part B and C might be a little bit simpler, but we'll move on and see what happens. So, part B. It says for x is between -2 and b, let h of x be the vertical distance between the graphs of f and g. Is h increasing or decreasing at x equals -0.5? Give a reason for your answer. Okay. Now we have our functions. If I were to just kind of sketch them again, it doesn't have to be perfect. But this is our function f. This is our function g, right? The vertical distance between these two, I'll just draw a straight line, is going to be f of x minus g of x, right? It's just our top minus our bottom function. That will give us the vertical distance. And they say that this is equal to h of x. Now the question asks us, is h increasing or decreasing at x equals 0.5? Now we know if a function is increasing, then its derivative will be greater than 0. So if h of x is increasing, then h prime of -0.5 will be greater than 0. If it's decreasing, h prime of -0.5 will be less than 0. So we just need to find the derivative of this function at -0.5. See what the value is. Now, once again, I have a really awesome tool in the calculator, this inderiv, right? Number 8 in the math section. If I click it, I can take a derivative at a point. So I'll do ddx and then plug in my function f of x minus g of x, which would be the ln of x plus 3 minus x to the 4th power plus 2x cubed. So that's just f of x minus g of x, and I will evaluate it at -0.5. which will give me h prime of negative 0.5. If I click enter, I evaluate it. It looks incredibly close to negative 0.6, right? I mean, down to like the decimal. So h of negative 0.5 equals negative 0.6. Therefore, h is decreasing at x is equal to negative 0.5. And that would be our final answer for B. So just write down something that shows that because the derivative is negative, it is decreasing. You could also put that in your justification. Say because h prime of negative 0.5 is less than 0, h must be decreasing at that point. Something like that. Super, super simple. I think B honestly wasn't too bad. But yeah, now we will move on to part C. Sorry, my phone died in the middle of part C, so I got halfway through it, then realized I had to restart it. So once again, starting part C, let's read it again. It says the region enclosed by the graphs of f and g is the base of a solid. Cross-sections of the solid taken perpendicular to the x-axis are squares. Find the volume of the solid. Okay, so we have our upper function f, then we have this lower function, which I continue to not be able to draw, which is g. And we're dealing with a cross-sectional volume, right? So our cross-sections are squares. And the base of the solid is going to be this distance between f and g, right? They're perpendicular to the x-axis. So if this side length of our square is the distance between f and g, it will be f of x minus g of x. And the most important thing to remember about cross-sectional volume is that to find the volume, I will integrate over my bounds of intersection, or whatever interval we're looking at. In this case, we're going from negative 2 to b, which we found earlier was 0.782, of our area of our cross-section, which in this case is just side length squared. So I'll do f of x minus g of x squared dx. And this integral will give us the volume of this solid. So to calculate this integral, I'll go to math, go down to number 9, where I can do a definite integral. I'll type this in, negative 2 to 0.782. And now I'll do my function minus my function squared. I'll put an extra parentheses because I'll remember I got to square it at the end. So ln of x plus 3 minus x to the 4th power plus 2x to the 3rd power. Now I'll put that extra parentheses so I can square it. I think my parentheses should be fine on both sides. I got 3 over there. Or I got 2 on the outside, and I got 2 on the outside there as well. Okay. So dx, I click enter, and I get that the volume of my figure is 5.34. And that would be the volume of this solid that we make using the cross sections. So just remember, if we're ever trying to find volume using a cross section, calculate the area of the cross section based on the functions and then integrate that area. Okay, so that is part C. Not too bad, honestly. Not a lot of calculator skills, just understanding what cross-sectional volume is. And then finally, we have part D, which we can always assume will be a little challenging. But let's look at it. It says a vertical line in the xy plane travels from left to right along the base of the solid described in part C. The vertical line is moving at a constant rate of 7 units per second. Find the rate of change of the area of the cross-section above the vertical line with respect to time when the vertical line is at position x equals 0.5. Wow. Okay, so we got a lot going on. So let's visualize this. I've got my upper function, and I've got my lower function, right? Okay. And basically it's saying there's a vertical line in the xy plane. So it looks like this. And it is traveling from left to right along the base of the solid, right? And it's moving at a rate of 7 units per second. And it wants the rate of change in the area of the cross-section above the vertical line. Okay. Now, I'm assuming, or it says that this is the solid in part C, and we know that our cross-sections were squares, right? So this was F, this was G, right? And we know that the side length of this squared was F of X minus G of X. And our area of this square, of our cross-section, is F of X minus G of X squared. Okay, so that's all information from the last problem. I mean, we could call this A of X, right? That's just my cross-section based on my position, X, right? Now it's saying that our X value is changing based on T. So I need to take the derivative of my area function with respect to time. So if I were to rewrite this as A of X, right? If I wanted to take the derivative of A of X with respect to time, I would need to think about this as an inner and an outer function. What's the derivative of A? Well, it's A prime. And then what's the derivative of X with respect to time? Dx dt. And that's just how fast we are moving in the X direction at a given time, right? Now they tell us we're trying to find our derivative, or our rate of change at this point, at negative 0.5. So this will equal A prime of negative 0.5 times our derivative dx dt, which is just the speed of the line, which we already said was equal to 7. So to find the derivative at the point, I can, for the final time, go to math and go down to my derivative calculator. So I'll go ddx, and then I will type in this function A of X, which is a little bit complicated, but it's not too bad. ln of x plus 3. I feel like we've typed this out a million times at this point. X to the 4th power plus 2x cubed. Add that extra parentheses because we need to square it. Seeing 2 there, perfect. We didn't mess that up. And we'll take the derivative at the point x equals negative 0.5. Okay? And this will give me the value of A prime of negative 0.5. I click enter, and I get negative 1.32. And I'll just multiply that by 7, which gives me negative 9.27. And this will be the rate of change of our cross-sectional volume, okay? And the units of this, it would be units squared, and I believe it was per second, right? Units squared because we're dealing with the rate of change of area. Per second, our units of time are seconds, right? So this one, definitely a complicated question. I would say specifically this step of taking the derivative of A of X, which is our function for, just area of this cross-section with respect to time, definitely challenging, right? But Once we realize that it's a prime of x times dx dt, plugging in these values is honestly not too bad, leading us to our final answer. But I hope that this video was helpful for you guys and taught you how to understand volume and area a little bit better. Like I said before, this one was challenging, but I appreciate you guys if you stuck it out, made it to the end of this video. I cannot wait to see you on the next one, and I will hopefully see y'all soon. Bye.